Till now in Maxima and Minima, we have discussed two concepts. First of all, you have seen the first fundamental theorem related to the concept of maxima and minima, and after that we have seen the concept of first derivative test to find the maximum and minimum value of a given function. Okay. Now today we will see the concept of second fundamental theorem related to the concept of maxima and minima. Actually, this second fundamental theorem is used to find the maximum and minimum value of a given function when the function has a value in a closed interval. So whenever the interval is defined, and particularly the interval is a closed interval, you have to think about the second fundamental theorem to find the maximum and minimum value of a given function. Actually, what are the important points which we should note while discussing this second fundamental theorem? Let us see here. First of all, you have to see the points where the first order derivative of the function, that is f dash of x, is equal to 0. Okay. So whenever in a given problem f of x is defined, first of all we will differentiate the function and find the first order derivative, and then equate the first order derivative of the function to 0 and find the value of x. Actually, those values of x are the points where the function will be either maximum or minimum. Okay. But in some cases you will see that whenever we will differentiate the function f of x, then its derivative f dash of x does not exist. So when f dash of x will not exist, even then we can find the maximum and minimum value of the given function. Okay. And then after that you have to look the given interval. Let us say if the interval is, let us say, x belongs to a and b, this is a closed interval, then the maximum or minimum value will be found at the boundary points a and b, and also at the critical points which lies between these two boundaries a and b. Okay. So noting all these 3 points, you can be able to find the maximum and minimum value of a given function. Okay. But this concept will be clear to you only when you will solve some numerical problems to clarify your concept. So I have taken here 3 important problems. The problems are very simple, and after the solution of those 3 problems, you will see that your concept regarding this second fundamental theorem will be crystal clear. Okay. So let us see what is our first example. This is just a very simple example to clarify your concept. The problem says that find the points of maxima minima of a function f of x which is equal to x cube minus 12x. So the given function is what? The given function is f of x, and we have to locate, or we have to find the points where this function will be either maximum or minimum. And the second part of the problem says that when you will find the points where the function is maximum or minimum, then you have to find what is its maximum value and what is its minimum value. Okay. So the problem has 2 parts. In first part, we will find the points where the function will be either maximum or minimum. Okay. And after getting those points for maxima and minima, we will find the maximum value of the function and the minimum value of the function too. So now let us see how we can solve this problem. As you know, according to the problem, the given function is f of x, which is equal to x cube minus 12x. So first of all, we will find its first order derivative. Okay. So its first order derivative, that is df by dx, which I have denoted by the symbol f dash of x, will be what? The derivative of x cube minus 12x. It is very simple function. You can say its derivative will be 3x square minus 12. Okay. Now, as you know, if this function f of x is maximum or minimum, either maximum or minimum, in both cases, this f dash of x will be equal to 0. So let us equate this f dash of x equal to 0. But you have found that f dash of x is equal to 3x square minus 12. So let us put here 3x square minus 12 equal to 0. And so you can say that 3x square equal to 12 and x square is equal to 4, and so x will be equal to plus minus 2. So there are 2 points which are x equal to plus 2 and x equal to minus 2, where this function will be either maximum or minimum. Okay. In fact, by knowing the value, you cannot say what will be its maximum value or what will be its minimum value, or you cannot say that when the function is maximum or minimum. For this, you have to check by the first fundamental theorem, by the sign of f dash of x. But here I am not going to check it, because our problem says that we have now to find what is its maximum value and its minimum value. So let us find the value of this function f of x at these 2 points, that is at x equal to plus 2 and x equal to minus 2. For this, what you will do? We will simply put x equal to 2 in this equation 1. Then you will get the value of this function when x is equal to 2. So f of 2 will be equal to what? This will be 2 cube minus 12 into 2. Okay. This will be 8 minus 24, which is minus 16. Okay. Now we will find the same function when x is equal to minus 2. So that has been written as f of minus 2, and that will be what? This is minus 2 whole cube minus 12 into minus 2, and this will be equal to plus 16, as you can see. So examining these two values, you can easily say that the maximum value of this function is 16 and its minimum value is minus 16. Okay. So this was a very simple problem, and I hope you have clearly understand its solution. Okay. Now the second problem is just related to this first problem. The second problem says that in the above problem, find the greatest, that is maximum, and the least, which means minimum, values of the function f of x when x belongs to the closed interval minus 1, 3. This problem is in continuation of the first problem. Here also this function f of x is equal to x cube minus 12x. Function is same. But now we have to find its maximum and minimum value when x belongs to this closed interval. Okay. So here we will need the concept of second fundamental theorem. Okay. Actually, by the use of second fundamental theorem, we can locate the point of maximum and minimum, and these points will be actually the critical points and also the boundary points, as I have told you. When I have told you that if you are given that x belongs to a and b, then while finding the maximum and minimum value, first of all we have to find the critical points. Critical points are those points which lie between a and b, and then we have to check the value of function at the boundary points a and b and also at the critical points. So first of all, in this problem, we have to find the critical points, and we have already learned about critical points in the previous lecture. And you know, for critical points, the first order derivative of the function, that is f dash of x, should be equal to 0. And you have already calculated in this first part of the problem that when f dash of x is equal to 0, then you have obtained that x is equal to plus minus 2. So I have directly written here that when f dash of x is 0, then x is minus 2 and plus 2. Okay. Now the given interval is between minus 1 and 3. So this minus 1, you can see this is less than minus 1. So this is outside of this closed interval. Okay. But this minus 1 is less than 2 and this is less than 3. So this number 3 lies in between the two boundary values of the interval. That is, this 2 is the interior point. So only this 2 is the critical point. You have learned the idea of critical point earlier, and you know from that concept that in this case only x equal to 2 is the critical point. So now when we have to find the greatest and least value of this function, we have to check, or we have to find the value of the given function at 3 points. And what will be those 3 points? The first point will be this critical point 2, and the another 2 points will be the boundary points. As you can see, the given closed interval is between minus 1 and minus 3. So minus 1 and 3 are the boundary points and 2 is the critical points. So we have to find the value of this function at these 3 points. That is x equal to minus 1, x equal to 2 and x equal to 3. And then we have to see that for which value of x our function is maximum and for which value it is minimum. So for the points of local and maxima and minima, x will have 3 values, and those 3 values are 2 boundary points and 1 critical points. Okay. So now let us find the value of our function f of x at these 3 points. Let us see. As you know, fx is equal to x cube minus 12x. So f of minus 1, this will be equal to minus 1 cube minus 12 into minus 1, and that will be equal to 11. You can see. Now we will find f of 2, and this will be 2 cube minus 12 into 2, and that will be 8 minus 24, that is minus 16. Okay. And at the third point, x equal to 3, the function f of 3 is what? This is 3 cube minus 12 into 3, and that will be 27 minus 36, and that is equal to minus 9. Now, observing these 3 values of the function, when x is minus 1, x is 2, and x is 3, you can easily say that among these 3 values, this 11 is the maximum value of our function. So you can say that when x is equal to minus 1, then our function is maximum, and its maximum value is 11. Okay. And among these 3 values, this minus 16 is the least value of our function. Okay. So when x is equal to 2, which is actually the critical point, at that very point our function is minimum, and its minimum value is minus 16. Okay. So I think after the solution of this very problem, the application of the second fundamental theorem is definitely clear in your mind. Okay. Now let us see another example, which is also a very important example to clarify your concept. Actually, this example says that this function f of x, which is equal to x cube minus 6x square plus 12x minus 8, does not have any points of local maximum and minimum. This point has no local maxima and minima. We have to check it. Actually, for testing that this function will not have any local maxima or any local minimum value. Again, first of all, we will find the point where the first order derivative of this function will vanish, will be 0. So your given function is this much. This is x cube minus 6x square plus 12x minus 8. And so if you find the first order derivative f dash of x, what will be that? That will be 3x square. You have to differentiate this equation 1. This is 3x square minus 12x and plus 12. This is the first order derivative. Now, we have to check that this function will not have any local maxima or minima. But for a time being, let us consider that this function is either maximum or minimum at x equal to x. Let us consider. So if the function will be either maximum or minimum, you know the first order derivative of the function f dash of x must be 0. So let us equate this f dash of x equal to 0. Now you can see that this f dash of x is equal to this much. So let us equate 3x square minus 12x plus 12 is equal to 0. Now you can take this 3 as a common factor, and the remaining terms will be x square minus 4x plus 4. Okay. Now as 3 is not equal to 0, so definitely the second factor x square minus 4x plus 4, that will be equal to 0. And x square minus 4x plus 4, this is just equal to x minus 2 whole square. So x minus 2 whole square is equal to 0. And so you can write x minus 2 equal to 0, and so that x is equal to 2. But let us see this the value of the function f dash of x changes or not changes when we pass through the point x equal to 2. For this, we will take a value which is smaller than 2, and then find the value of f dash x. And again we will take a value which is greater than 2 and find the value of f dash of x. So for example, let us find a value here. Let us find f dash of 3. It means we are taking the value of the function f dash of x when x is greater than 2. Okay. For example, in this figure, let us say here there is a point x equal to 3. And as you can see here in this equation 2, f dash of x is equal to this much. So what will be this f dash of 3? This will be 3 into 3 square, okay, and minus 12 into 3 plus 12. What will be this result? You can see this is 9 into 3, this is 27 minus 36 plus 12, okay, plus 12. Now, what will be the result? You can see here 27 plus 12, this will be 7, this will be 9, 3, 39, minus 36, this will be plus 3. It means f dash of x is positive when we take x greater than 2. Okay, this is positive. And you can also see from this curve which I have plotted here for the function f of x, that when we will take a point here and draw a tangent, this tangent will make an angle which is less than pi by 2, and so the slope will be positive. Okay. Now let us find the value of f dash of x when x is less than 2. Let us say f x is 1. For 1, what will be the function of what will be the value of function f dash of x? You can see this will be 3 into 1 square minus 12 into 1 and plus 12. What will be this? This is 3 minus 12 plus 12. and you can see this is also 3, and so this is positive. So what you are seeing here, when we pass through this point x equal to 2, the sign of f dash of x does not change. And if its sign does not change, what does it mean? It means the function has no local maxima and minima. Actually, this is just a monotonically increasing function, because you can see when I have increased the value of x from 2 by 1 and taken x equal to 3, then the function f dash of x is equal to 3. And when we have also decreased the value of x by 1 from 2, then again it is 3. It means this function is monotonically increasing. Okay, and that's why we can say that this function has no local maxima or minima. Actually, I have written here that when f dash of plus 2 plus 2 plus means what? 2 plus means you have to take the value of x which is greater than 2. Then you say that this derivative, that is f dash, is actually positive, that is slope of the curve is positive. Okay, and when we take x less than 2, so, symbolically I have written f dash of 2 minus. 2 minus means a value of x which is smaller than 2. Then again we see that this f dash is greater than 0, that is positive. Okay, and I have taken the proper example, taking x equal to 3 and x equal to 1, and you have seen the same result. So you can say that our function does not, so the first order derivative of our function f dash of x does not change its sign while passing through the point x equal to 2, where f dash of x is equal to 0. And so you can say that this function f of x has no local maxima or minima. Okay, and as I have told you, actually this function given in our problem is just a monotonically increasing function for x belonging to R. Okay, so I think after the solution of these three problems, that there must be have a clear-cut idea of the concept of maxima and minima on the basis of second fundamental theorem in your mind. Thank you very much.